Welcome, fellow chemists, to this first of 3 videos on the Reactivity-Selectivity Principle, which is a follow-up on the radical substitution video. We were previously introduced to the halogenation process, and on a molecule of methane, the halogen, be it bromine or chlorine, will replace one of the hydrogen atoms. Although it looks to us like it can remove 4 different hydrogens and produce 4 different products, that is not the case. Whether bromine or chlorine is involved, only one product is formed. Even if we switch the molecule to ethane, which was the molecule from the previous video, it has 6 hydrogens where substitution can occur, but the result is the same. They look different in 2 dimensions, but in reality every product is identical. What we can conclude is that radical substitution of a single halogen on methane or ethane results in only one product. However, if we switch to propane, the result is more complex to explain. So why is the result more complex? Well, a quick glance at the molecule should be enough to see the left side and right sides are identical, but if that is not obvious, take a look. The carbon on the left is bonded to 3 hydrogens. This is also true for the carbon on the right. Still not convinced? Let me make a copy of the leftmost carbon and its hydrogens. A bit of rearrangement, but crucially not adding any atoms or creating new bonds, and we see it overlaps nicely. The 2 ends are identical. While they look identical, that is not enough to make them chemically identical. To check that, we need to see what those sides are bonded to. If they are bonded to the same things, then they are chemically identical. The left side is bonded to the CH2 in the middle, and the right side is bonded to the same CH2, which means both ends are chemically identical. It should come as no surprise that the CH2 in the middle is different, as it is bonded to 2 CH3 groups. This means it is chemically different from the ends too. Since we know that radical substitution results in a halogen replacing a hydrogen, we need to be able to tell these positions apart in order to understand which products form. So if monochlorination occurs by random chance, then we would expect a chlorine atom to end up substituting any one of the 8 hydrogen atoms on the propane. It could either replace one of the 6 identical hydrogens on the end of the molecule, or either of the 2 in the middle. So with 6 hydrogens on the ends, and 8 total, we would expect the chlorine to substitute on the ends 75% of the time. This would mean the remaining 25% of the time it would end up in the middle. So if we tried this with chlorine, we would expect 75% of our product to be 1-chloropropane, and the remaining 25% 2-chloropropane. However, experimentally, product distribution is closer to 45% 1-chloropropane, which means the remaining 55% is 2-chloropropane. Clearly, something strange is going on, so let's take a closer look at what is happening. To understand the result, we first need to look more closely at alkyl radicals. Methyl radicals are when the lone electron is on a carbon atom bonded only to hydrogens. If this carbon with the electron is bonded to one other carbon, it is considered a primary radical. If it bonds to 2 others, it is secondary, and if it bonds to 3 other carbons, it is tertiary. In terms of stability, methyls are so unstable we don't even consider them, and primary radicals are the least stable, while tertiary radicals are the most stable. The more stable radicals are easier to form, and hydrogens in those positions are more likely to be substituted. Now, instead of writing out these words all the time, we can use a symbol. The symbol is composed of a number and the degree sign. So for primary, we use the number 1, and a hydrogen in that position is considered a primary hydrogen, and the carbon is considered a primary carbon. With secondary, the idea is the same, except the symbol now has the number 2. And of course, for tertiary, this means the symbol will now change to the number 3. So when we look at a propane molecule, what radicals do we form? Well, let's first assume all these hydrogens are unique, and if we remove any of the hydrogens on the end, we will create a primary radical. And if we remove either of the 2 in the middle, we will make a secondary radical. The breakdown of the 8 possible radicals that can be produced should seem very familiar. So you might be thinking, didn't we know this already? And yeah, we did, but what we need to know now is which of these radicals the chlorine forms. In order to know which radical the chlorine forms, we first need to look at its reactivity. It turns out that the very reactive chlorine has no real preference for what type of radical it forms. This molecule is not propane, obviously, but let's pretend the first carbon labeled is the one and only primary position. As a guide, the rate of formation of primary radicals is considered 1. Now, since the location of the primary radical is where the chlorine is going to end up, that means the rate of formation of primary products is also 1. Due to their stability, chlorine forms secondary radicals more easily, and therefore secondary products more easily, at a rate of 4 times that of the primary. Finally, tertiary radicals are the most stable and are produced at the highest rate of roughly 5 times that of the primary. This also informs us that chlorine, which we know from general chemistry is very reactive, is not very selective and produces the various radicals and products almost uniformly. Okay, so now that we have seen the behavior of chlorine, what about bromine? Since this is still a molecule of propane, the number of primary and secondary hydrogens is unchanged. The results you would expect if monobromination was down to chance is still 75% in favor of the primary product 1-bromopropane, and the remaining 25% will be the secondary 2-bromopropane. However, the experimental results are much different, where only 3% is the primary 1-bromopropane product, and the remaining 97% is the 2-bromopropane. Clearly, bromine must behave radically different than chlorine. So now we need to take a closer look at bromine's reactivity and what type of radicals it tends to form. Using the same example from before, we can once again pretend this first carbon labeled as the one and only primary position. Just like with chlorine, bromine's rate of formation of primary radicals is also considered 1. This means the rate of primary products is also set as 1. Due to their stability, bromine forms secondary radicals more easily, and therefore secondary products, but at a much higher rate than chlorine of 82 times that of the primary. Finally, tertiary radicals, being the most stable, are produced at the highest rate of 1,600 times that of the primary. Bromine, which is less reactive than chlorine, is much more selective about which radical, and therefore which product, it forms, and we can see this with the potential distribution heavily favoring tertiary. In summary, the reactivity-selectivity principle tells us the more reactive chlorine is less selective and therefore has no preference for which hydrogen it removes. By contrast, the less reactive bromine is more selective, which means it heavily favors the removal of tertiary or secondary hydrogens. Though it suits us well here, we cannot apply this idea in general for all reactions, and this is unfortunate because the RSP is a simple inverse relationship that seems quite sensible given the evidence we have seen so far. As is the case in many things organic, it is just not that simple, and even the IUPAC Gold Book states the validity of the RSP is a matter of controversy. That puts it rather nicely when compared to a 2006 article which calls it an imperishable myth. While RSP applies in this case, Hammond's postulate does a better job of explaining the results referred to in this video more generally, so check out this crash course video on how it applies to radical reactions. Link in the card above and description. However, not all is lost, because we can use this idea to actually predict those seemingly anomalous experimental product distributions for the chlorination and bromination of propane, and we shall do that in part 2. Thank you very much for watching. If you enjoyed this video, please like and subscribe as I have more in development. With today's video focusing on the potential outcome of radical substitution, I must recommend viewing the first video on the mechanism of the reaction itself. As always, feel free to get in touch with me via email, social media, or if you would like, make a request in the comments.